It's seldom that we can interface a signal straight from the real world directly into a neural net. The nets that we've looked at so far require an input in the range from 0 to 1, so at the very least we need to ensure that our external signals fall into that range. Let's start by looking at a general algorithm to normalize a set of inputs to fall between 0 and 1. As an example, let's use an image. Firstly, find the value of the lowest and highest pixel in the image. Say for example that the lowest value is 0.2 and the highest is 0.8. Secondly, find the maximum range. This is the highest value minus the lowest one, so in our case it's 0.8 minus 0.2, which is equal to 0.6. Next, subtract the lowest value from all the pixels. Say, for example, we had a pixel of value 0.5, then this would be 0.5 minus 0.2 is equal to 0.3. Do this for all the pixels. Finally, divide all the resulting values by the range which we calculated earlier. In this case, that would be 0.3 divided by 0.6, which would be equal to 0.5. Quite often, if the information is in some standard data or file format, then it must be processed in order to retrieve the basic data. Typically, this means decompressing the file, and special algorithms are available to do this. For example, for image files, these are listed in the Encyclopedia of Graphics file formats. Headers and footers are then removed and the values normalized as already described. In terms of images, compressed file formats include JPEG and uncompressed ones include RAW. So RAW files are fairly easy to process. Just processing the numbers in an input set is usually not enough, however. We often need to do other processing. One important aspect of this is the framing of the data, and understanding this illustrates perhaps the biggest problem with simple neural networks. You may have wondered why, if neural nets are so good at recognizing patterns, they are not used to guide automatic robots everywhere, and why therefore we haven't entered a new age of intelligent machines. The answer to this question is that neural nets are the best known technique for this, but only when the data is correctly framed for them. The diagram now on the screen illustrates this. In terms of a waveform or time series data, this is equivalent to someone speaking slowly, for example, if it was voice recognition, or speaking in a higher or lower pitch. So simple neural nets are good at recognizing such framed data, but very bad at recognizing, say, for example, a face in a crowd. One way around this with such simple networks is to window and scan the image as shown in the diagram on the screen. Eventually the pattern will fall exactly into the window. However, such networks must be carefully trained to avoid false positives, where the network misrecognizes noise as an image. It should be noted, however, that this is a slow process and quite complex to code. We also need to decide exactly what data to present to the network. To see what I mean by this, let's go back to the waveform example which we discussed in an earlier video. As we previously discussed, this could be fed into the network as shown by sampling the data. Or alternatively, we could extract information from a waveform using, for example, a Fourier transform, and then feed its amplitude, frequency, and harmonics and phase into the network. Doing this and transforming the data from one domain to the other in order to make the network recognize it more easily is a critical decision to make when you're deciding how to make your network. All these points need to be carefully considered when designing one's network.